Okay, so you'll see me, you guys are going to see me run a calculator some. That's okay. But I figure you need to see that here, and that was a nice place to break the video. So we're getting H1 of, based on this information, we're getting H1 of about 271.22. I'm going to assume you know how to interpolate. If not, you need to learn how to do that. Okay, that's not going away. Now, I apologize, the sun is not helping me here. My blinds block most of it out. You can see I'm getting a little bit in there. Anyway, so let's see what else we got here. What we're trying to do again. Right. Trying to find COP, Q dot L. Find COP, I need QHL, or I'm sorry, Q dot H. I've got the power input already. Now I've got enough information to find Q dot H. Okay. So, Q dot H is equal to the M dot that's given times H1 minus H2. And given that, then Q dot L, one of the things that's being asked for, Q dot L we can find as Q dot H minus W dot N. So we find QH here minus the work input, that gives us QL. And then finally, COP for the heat pump is going to be also the Q dot H that we find divided by the work input. Okay? All right. Now I've got the solutions here. So that's how we would get there. Assume you guys can run calculator on your own time. Right? So yes, we can treat each of these components in the diagram as its own system. Here we treated the condenser as its own system. If we know the properties at the inlet and outlet of the compressor, we can treat the compressor as its own system, or the evaporator, or even the expansion valve. We can treat any of these as their own little system. And then we can do a first law analysis on those smaller systems. Here we're doing the condenser. And so you can see, right, H1, H2, we've already looked those up. We've got those, had those up above. Find Q dot H. Based on those properties, we find Q dot H to be about 3.164 kilowatts. Okay. Let's see. We find, yeah, so Q dot L then would be 1.96 kilowatts. COP, you can see there is 2.64. Okay. All right. So from there, we move into starting to talk about Carnot cycles, Carnot devices. To do that, we need to make sure we understand what is a perpetual motion machine. A perpetual motion machine is any device that could, in theory, operate perpetually. It could just continue on without any outside influence. These don't exist to the best of our knowledge. And it would require a violation of either the first or the second law as they stand, as we know it. So a cool example is, let's say I've got a pump that runs high pressure output into a turbine. That turbine generates work, that powers the pump, and then the output of the turbine is a low pressure output running into the low pressure input of the pump. Pump increases pressure, causes the turbine to turn, that turns the pump, etc., etc. We could hook this up, inject really high pressure fluid right here at this point and let it go, and it would run for a little while. Depending on how good your bearings are in here and here, this may run for a while. You just use compressed air. It's not going to run indefinitely. For it to run indefinitely, for it to run perpetually, it would have to violate the second law. And we're going to see in the next chapter, we can describe in detail how this is going to work. For us right now, it's just okay to understand that, no, you can't operate this thing perpetually. Here's another one I like. This one violates the first law. Right? Cool idea. Let's take a regular heat engine that we just saw, and instead of supplying a heat source that we're going to have to pay for, unless it's the sun, to the boiler, let's just replace that heat source with a resistance heater, and let's just take some of the work or the power output off the turbine and hook that right into the boiler, and let's just do that. Save a step. Well, here's the problem. What crosses the boundary? Right? If you look at what crosses the boundary, well, I've got minus, let me get this stylus here, minus Q dot out minus power out. And if it's a cycle, that's going to equal 0. So minus is equal to 0. No. That can't work, right? There's nothing going in. Something has to, if both of these are going out, something has to go in for the energy balance to stay at 0. And so that's just not going to work. Why do we talk about this? Well, a couple of reasons. Again, it leads us into the idea of a Carnot cycle, right? But it's also important to note that there was a time where you could just send off cool ideas to the patent office, and they might grant you a patent, and you have a certain amount of time to figure out how to do it. Today, they don't do that. One of the first things they'll do is they'll analyze to see if your design violates the first or second law of thermodynamics before issuing you a patent. Okay? Now, there is a limit. There's a point at where we can get just right to just shy of being a perpetual motion machine. We call that a reversible process. A reversible process, again, direct quote from your text there, a process that can be reversed without leaving any trace on the surroundings. Now, it's really easy to get a system back to its initial state. Right? I normally keep some cup of water here next to me, and it's normally chilled. So that water that's sitting there now has warmed up. I could get that water back to its initial state. I could get it back cold again. That's easy. The problem is, to do that, I have to leave a mark on the surroundings. I can get the system back to its initial point. I can't get the surroundings and the system both back to the initial point, because everything we're doing is irreversible. But the reversible process is the limit. The reversible process would be one where I could get both the water in my cup back to its initial temperature and not have the environment around it or the rest of the universe at any higher of a temperature as a result. So it's a limit, and that's kind of the best, the absolute best we can do. Now, there's two things that prevent us from reaching that limit, reaching that goal. We call those irreversibilities. And really, there's multiple ways, there's multiple forms that can come in. Okay? Friction is kind of a common idea. Right? Generating heat from good motion, that's friction, but we do require friction in order to be able to move. So it's a common culprit, but it's also a good thing. We do need friction sometimes. We use it to our advantage. But electrical resistance, so electrical resistance is kind of like friction for flowing electrons, electricity. That generates irreversibilities. If I take pure oxygen and pure nitrogen and mix them together in the right amounts, I get essentially breathing air, atmospheric air. But to get them both back to their initial states, to get both the air, both the nitrogen and the oxygen back to its initial values or visual concentrated forms, I'm going to have to do some work to get there. I'm going to have to leave a mark on the surroundings, and that's going to be irreversible. So, all right, so that is that set. Yeah, this card's fine, so let me go back here. Like I said, those were the kind of the end of the 16 there. Let's look at the 17 notes here. As we talked about these. There we go. So, why that's important? Well, our good friend here, Pierre Sadi Carnot, French military engineer, if I'm not a history person, I'm sure people are going to tell me in the comments that I'm wrong here, but if I'm not mistaken, I believe he was a military engineer in Napoleonic times, trying to figure out, hey, can we figure out the most efficient engine that we can use to conquer our enemies? And he put together a thesis or a dissertation, and in that, he proposed this reversible cycle. And the most efficient cycle that to this point had been proposed ever. I don't know, maybe that's not the best way to say that. It comes in a number of steps here. We call this the Carnot cycle. Now I'm going to draw these out. Okay. But the Carnot cycle, you don't have to write this yet. But it's going to go through an expansion, compression, compression. Isothermal meaning constant temperature. Adiabatic meaning no heat transfer. These are not the same. I can have temperature change with or without heat transfer. I can have constant temperature. I can remove heat to maintain a constant temperature as I increase or decrease pressure, and that's what we'll see here. Okay. Carnot, the big thing though, what really made this the most important is Carnot proposed all of these processes would be reversible. If you could figure out how to do this in a reversible fashion, this would be the best possible version of an engine that one could construct. So, I'm going to stop there. That's going to be kind of a nice stopping point. We'll start the next video right here at this point. We'll get all of this entire Carnot cycle in the next video.